Hi, back with me Wulandari in algorithm strategy class. So here in this video we will continue our discussion about branch and bound. This is the second part of branch and bound video. So in the first video you can watch the talk about general description and also its example for job assignment problem, and in this video we will talk about the use of branch and bound to solve a discrete knapsack problem. Okay, let us get started. So you should familiar already with a discrete knapsack problem. So basically we are given an object and also a knapsack, and the knapsack has a maximum capacity of K, let's say, and every object I we have has weight property Wi and also profit property Pi, and each object cannot be divided. That's why we called it discrete knapsack or 0-1 knapsack. And we want to know which objects should we put in the knapsack so that we obtain the maximum profit, and of course we do not exceed the maximum capacity of the knapsack. And the solution can be represented as a tuple like this, where x1 is 1 if object 1 is put in the knapsack, or 0 if it is not put in the knapsack. So how can we build or construct a state space tree for this problem? For 0-1 assign knapsack problem. So let us consider a discrete knapsack problem with an object and maximum capacity of K, and where the solution of the problem is written like this, like we described before in the previous slide. And here we can construct the partial solution by determine the value of x1, next the value of x2, and so on until finally we have the value of xn, which means the level in this state space tree represent the order of items we check. So level 1 will determine whether x1 is 0 or 1, and then level 2 will be the space for determining whether x2 is 0 or 1, and so on. Other than knowing how to construct a state space tree, for branch and bound we also need a way to compute a bound for this problem. So discrete knapsack problem is a problem to maximize the total profit. So it is a maximization problem, which means here we need to compute an upper bound for each partial solution. So again, we know that we can represent the solution for this problem as a tuple x1 to xn, and here for knapsack, recall in greedy we know a property called density. Let's say density is D, so density of item I is the profit of item I divided by the weight of item I. What does it mean? It means the value of an item per weight. So for each weight unit of the item, we can obtain the profit of DI. Then the maximum profit we can obtain for the discrete knapsack problem cannot be more than K times maximum of D1 until Dn, right? Because the maximum density we have is D, let's say, then the maximum profit we can have for the problem will be where we put the item with maximum profit to the knapsack and make the knapsack full of it. So the maximum profit we can obtain cannot be more than this. And since we always need to know the maximum density from the items we have or we haven't checked yet, then we should sort the items based on their density in descending order, so that the first item, density of the first item is not less than the density of the second item, and so on until the last item. So the lower bound for each partial solution of this, so for example, we already determined what is the value of xi for I equals to 1 to k, but not for the rest. Then we already know the total profit we have so far until the kth item. And then for the rest one, we can check the remaining capacity we have, and then we multiply it with the largest density we have on the remaining items. And because we already have we have sorted the items based on the largest density first, then the next item will have the largest density. So that's why we multiply it with the density of the next item. Let's get started with the example. So for example, we have four objects, A, B, C, and D, with and a knapsack with maximum capacity of 10. So the first step, the initial step here, we need to sort the objects based on their density. So here we have density of 4, and then density of 6, 10, and 5. Next, we sort them based on the density. So the first one will be item C. The next one will be item B. The next one will be item D. And the final one will be item A. Like this. Okay, so we have sorted the items, and we start with the initial node where we haven't decided anything on the problem. So the solution has not contained anything. So it means we have not chosen any objects, which means that the total weight we have up until now is 0, and the total profit we have up until now is also 0. And upper bound, and its upper bound, then the remaining capacity we have, which is 10, k minus w, which is 10 minus 0, which is equals to 10. We multiply it with the density of the next item. So the next item will be C here, which has the largest density. So we multiply it with 10, which is equal to 100. So we have 100, which is the only leaf we have so far. So we check the children of the node. And the children will be either we choose the first item or not. Then if we choose the first item, then our weight will be 4, the total weight we have so far, and the total profit we have so far will be 40. And the upper bound will be 40. Here the total profit we have so far, because we already know that the solution must contain the first item, which give us the profit of 40. Plus, we still have 6 capacity remaining, which is 10 minus 4. And it can be filled with items that has density no more than 6. Okay, there's no other items that has density more than 6. So we times the remaining capacity with 6, so it is equal to 76. It is the same for the next option. The total weight we have so far is 0, and the total profit we have so far is 0, which means at this point we don't have any profit yet. But we still have 10 capacity remaining, which means the 10 capacity remaining can be filled with items with density no more than 6. So we multiply it with 6 so that we have 60 as the upper bound. So here this problem is maximization problem, and we have upper bound for two leaves we have here. So we need to compare which one give us the best result. And because it is maximization problem, the best result means the biggest upper bound we have. So the biggest one is 76. So we check the next children of the node. So for the second level, we can check whether the second item is chosen or not. So if it is chosen, then we will have weight of 11, which is larger than the maximum capacity, so it is not feasible. And for the next option, we check the case where the second item is not chosen. So here we will still have the total weight of 4 and the total profit of 40, and the upper bound will be 40, which is the profit we have so far, plus the remaining capacity we have, which is 6, multiplied by the largest density we have, which is 5. So 70 is the upper bound we have here, and for the two active leaves we have 60 and 70. We check the largest, we choose the largest upper bound, which is 70, so we check its children next. So we check the third item, whether we choose it or not, and check the total weight, total profit we can have, and also the upper bound, which is the total profit we already have, plus the remaining capacity, which can be filled by the item that has density no more than 4 here, which means the upper bound is 69. And for the next option here, again, we have total weight of 4 and total profit of 40, and the upper bound will be total profit we have so far, plus the possibility to fill up the remaining capacity with the largest density we have up to this point. So the remaining capacity is 6, and the largest density we have is 4. So the upper bound is 64. Again, we check from all active leaves which one gives us the better upper bound, which is 69. So we check its children, which leads us to final solution 1011 and 1010. So we check the weight and the total profit. The first one gives us a non-feasible solution, and the next one give us a total profit of 65. And if we see the other leaves we have here, 60 and 64 is not better than 65. It means that even if we continue this node, then the final solution will not give us better result than 60. And for this one, even if we continue this partial solution, then the final solution will not be larger than 64, which means 65 must be the largest profit we can have, which is given by choosing object C and also object D to obtain the total profit of 65. Okay, that's all for discrete knapsack problem. For the next video, we will talk about the branch and bound strategy for traveling salesperson problem. Okay, thank you for watching and see you on the next video.